In this chapter, we will talk about the pharmacokinetic of extravascular route of administration, with more emphasis on oral absorption or oral route of administration. But we will talk in general about extravascular kinetic, and we are going to talk about single dose of extravascular route of administration, and also with one compartment kinetic. We will talk about linear kinetic, but before we reach this point, we will talk a little bit about some information that you need to know about the extravascular kinetic. When we talk about the site of action or the route of administration of the drug, we can divide it to intravascular and extravascular routes of administration. And from the name of it, when we are talking about intravascular, it means inside the vascular system, such as intravenous, either intravenous as bolus or intravenous as infusion, okay, or intra-arterial, okay. When we are talking about extravascular, it means that it's outside the vascular system. So anything that is extra or outside this system or the vasculature is called extravascular route of administration. We had an example of intravascular system, the IV bolus so far, and we will talk about IV infusion later. In the intravascular administration, again, as I said, it could be intravenous or intra-arterial. We know that according to at least what we know from the one compartment model, that we didn't had any absorption. We didn't had any absorption process. We had nothing here, so the drug directly entering the body, and here it's represented by one compartment. So we don't have any absorption, or in some of your references you'll find it they consider it as 100% absorption, or in other words, it's 100% available in the systemic circulation, okay? Because the drug is directly entering the vascular system. We had immediate onset of action, and this when we had it similar, if we are talking about profiles, when we are talking about concentration in the plasma versus time, rectilinear, we will have this. So the whatever the effect that we have, we directly have it, because as the amount, which is the doses given, is directly entering the system. So our CB node was the initial concentration that is we have according to the initial amount that is taken, which is the dose. And the immediate onset of action, this is what we mean about it. If you have minimum effective concentration, right, here the effect will be directly at time equals 0, because again the drug is entering the systemic circulation directly. The entire administered dose is available to produce pharmacological effect. The entire administered dose, which is X naught, as I mentioned here, because we have 100% of my drug reaching the systemic circulation, so it's available to produce the effect. When we are talking about different routes, we could have either parenteral route of administration or anterior routes of administration. When we are talking about parenteral, it means anything that is related to injections, okay? An examples on the parenteral routes, we have IV bolus, IV infusion, IM, and sub-Q. When we have interior routes, which is anything that is not related to injections, such as sublingual or oral and rectal route of administration, in addition to different other routes such as transdermal and pulmonary or intranasal. Okay. What I want you to know from here that according to different routes, and again, if we are talking about parenteral routes, it doesn't mean that I'm talking about intravenous routes, right? Because both of this and this are intravenous, but this and this, for example, they are extravascular. So it doesn't mean if the route is parenteral, it's intravenous. And now this by just seeing the examples of intravenous routes of administration compared to parenteral routes of administration. Whatever the routes that we have, parenteral routes or anterior routes, we know that the bioavailability, if you see each and every one, is variable according to the route of administration, so it's dependent on the route that we are taking, and also the advantages or disadvantages of the route of administration depends on the drug delivery that is related to the route. What I'm interested in here is if you look at the bioavailability for IV, we can see that it's complete and 100% for IV bolus, and it's the same for the infusion. And why is that? Because the drug is directly entering the systemic circulation. So it's when we are saying it's completely bioavailable, it means it's available in the systemic circulation. For IM and sub-Q, it depends if we are talking about aqueous solution rather than oily solution or non-aqueous solution, and the same thing for the sub-Q. So it depends on the formulation that we have, but usually it's higher when we compare it to other routes of administration. But again, it's all related to the formulation that you have. The buccal or sublingual, for example, it's rapid when we are talking about lipophilic material or lipophilic dosage form. When we are talking about oral, it depends on the formulation that you have, on the target site of the absorption, and so many things that relate to biopharmaceutics of the drug and the site of absorption. Again, for rectal, it's again variable, and it depends on the formulation that we are taking, and depends on if we compare to other intravenous or extravascular route of administration. So the variability of the bioavailability depends on the route of administration and depends on the absorption process, if it's the extent and rate of the absorption process, if it's slow, if it's rapid, if it's high, if it's low, it depends. Okay, and we know for the transdermal, it's usually with a slow absorption because we have a high thickness or large thickness of the membrane. When we are talking about nasal or pulmonary, usually the absorption is rapid, and this is one of the advantages of the pulmonary or intranasal absorption. But we have some major challenges for the pulmonary and intranasal drug delivery, because usually we have problem of delivering the drug or the formulation to the lungs or the intranasal passages. So it's the problem with the absorption from the pulmonary system is not the absorption itself as a process, because the thickness of the membrane is very low. So it's rapid absorption, but the issue is with the challenges of the delivery of the drug to the lung or the intranasal system or intranasal passages. When we are talking about the extravascular route of administration, again, anything that is outside the vascular system. It could be oral, it could be IM, it could be sub-Q, sublingual, buccal, rectal, transdermal, pulmonary, anything. Anything that is the administration is outside the vascular system. Okay, but in kinetic wise, if we are talking about the same model in this case or in this chapter, we will talk about one compartment single dose. It would be the same. We can deal with it whatever the route of administration, but we are just having different route of administration. But you will have more emphasis on the oral route of administration. Okay, so we will talk a little bit or more about oral, but it's valid for any other extravascular route of administration. When we are talking about extravascular route of administration, we will have one process, one kinetic process that is extra compared to the IV, which is the absorption. So if we are talking about one compartment model, so we have this, which was really related to elimination, as we know already, and we have this, which is related to absorption, which is a new process because we are talking about extravascular. So we have the absorption. Okay, the onset of action depends on many physiological variability related either to the drug itself or the physicochemical properties of the drug, the route of administration, in addition to other physiological factors that is related to the targets of the absorption that we are interested in, which was what we call it biopharmaceutics as a science. Okay, so the onset of action could be direct, could be not. It depends on many factors. Okay, the entire administered dose may or may not always reach the systemic circulation, which means if we are talking about bioavailability of the drug, it could be 100%, maybe less. So it could be equal or less 100%, depends on the how much or how the rate and extent of the absorption of the drug or reaching the systemic circulation. Okay, so those are one of the or examples of the major changes or major differences between the extravascular and intravascular route of administration. Those two profiles are important if we want to compare the one compartment versus two compartment if we are talking about extravascular. And let me draw it from scratch here. If we are talking about, again, concentration in the plasma versus time in extravascular route of administration, this is our profile. It will be something similar to this. Start from 0, and this is the max, C max, and T max, and then this will continue to decrease until we reach 0 at time equal infinity. Okay, so this is the what you will see if you are on rectilinear linear profile. Okay, if you change it to a similar profile, concentration versus time, you will have this until you reach C max. So if I change this to similar profile rather than rectilinear profile, you will have this, then you will have this profile. After C max or T max, you will have a linear profile that is presenting what? Your terminal phase, or in this case, the elimination. If you have two phases, let's say here, absorption phase, which is represented before the Cmax, and elimination phase, and after you after the Tmax or Cmax, you reach the Cmax, the profile is shown as linear, then you are talking about an example which is similar to whatever you have in here in this slide. We are talking about two phases total, but you have one post-absorption phase, which is related to elimination. Then this is an example of a one compartment model, which means it's similar to this. Okay, and you have elimination here and you have absorption here, but it's one compartment. What do we mean by what I mean by one compartment? We said that if you have one compartment, which means that the distribution reach rapid equilibrium in all the organs and tissues and the body. That's why we can have it in one compartment. That's why you have only one process after the absorption, one phase, sorry, after the absorption phase that is clear and obvious. Okay, if we have the again, if you have concentration versus time profile on rectilinear, and you will have this profile T max, C max on rectilinear. Okay, again T max, C max. If you change it to semilog profile, concentration versus time profile, and you'll have this until maximum, then you have something that is deviated from linearity, and then you'll have this another linear profile, which if we are talking about phases, okay, let me use another color. You'll have something until the maximum, okay, and you have one this phase that is after the absorption phase, and you have another phase. So we have the absorption phase. Again, this is when you change it to semilog to visualize if you have only one compartment or not, one linear phase or not. So we have absorption phase, we have distribution phase, and you have elimination phase, or what we call it the terminal phase. Okay, the last phase that you have in your profile. Okay, so again, which is similar to whatever that you have in here, okay, on semilog profile, and we have absorption phase, distribution phase, and again, either you have post-distribution phase or elimination phase. And if we are talking about post-absorption phase, you have two post-absorption phase, that is one related to distribution and post-distribution. Okay, total phases that you have here is 3 phases, and total phases that you have here is 2 phases, right? And why you have it in here? Because which is similar to this, because the drug is, this is the similar model or example of the model that will be presented by this profile. This is the first compartment, this is the second compartment. So not all of my drug is rapidly distributed in the in a number of organs or tissues, but some of them, but part of it, let's say part of the drug is slowly distributed to other part or other tissues or other organs, and the distribution equilibrium needs time to be reached between the first part and the second part. So this is what we can see in this part, which is related to distribution before we reach the equilibrium that we can see it in the second part of the other phase or the terminal phase. Okay? Again, just to summarize, if when you change, this is the profile that you have whatsoever, if you're talking about one compartment or 2 compartment, okay? What you can, then after that, you need to detect if you have 1 compartment or 2 compartment. If you have 1 compartment, it means that you have, other than the absorption phase, another phase that you can detect kinetic-wise, okay? So that's why you see the absorption phase, and that's why you see the absorption phase and the elimination phase, okay? And the distribution is very rapid in my compartment to an extent that I can detect it. It's not that obvious. It's rapid, so the drug is rapidly distributed in the compartment that we have. When you have 2 compartments, you have the absorption phase, you have something that is related to distribution, and something related either to the elimination or total elimination from the compartment. Okay, so even you have it as this on rectilinear, still when you change it to semilog, you can detect whatever is the phases that you have. That's why when we were talking about, when you were keep asking me why we change it to semilog, that's why you can detect if you have one linear phase or you have many phases, so you can detect if you are having one compartment or many compartments. So because we have absorption phase and we have something is happening after the maximum, which is deviation from linearity that is related to distribution phase, and then post distribution or elimination phase or terminal phase here. So you have an idea that it's not only one compartment, it's not only a rapid distribution. We have some organs that the drug is slowly distributed to it, and we need time to reach the distribution equilibrium. Okay. In our model in this chapter, we will have if we are talking about oral route of administration, you have the amount in the GI, or you will have it as XGI. Then we have a kinetic process that is related to absorption. We have a kinetic process that is related to elimination. We have amount in the body as dB or XB. We have a barren volume distribution. We have amount eliminated or XE. Okay, so again, you may have this amount also as XA in other references. Okay, you can we have this if we are talking about first order as Ka, which is absorption rate constant. If it's first order, it will be 1 per hour or 1 over hour as a unit. The elimination, if we are talking about elimination rate constant first order, again, it will be 1 over hour, 1 per hour, and it will be the sum of what is related to excretion plus what is related to metabolism. And you know this by now. Okay, and we will talk about the details of this when we are talking about this in kinetic terms. Okay, if we are talking about the amount of the drug, again, amount of the drug, let's say, not all of them, amount at certain time, because we have many profiles, so it could be XP or not, okay, versus time. We will start with this profile, which is what? So far, you know that it's amount in the body at certain time. So amount of the drug available in the body or remained in the body, okay? When we are talking about the amount, a cumulative amount excreted unchanged, it's similar in the shape of whatever you know, excreted unchanged. The metabolite, okay, excreted in the urine also. So this will be amount excreted in the urine of the drug at certain, it's cumulative, so at certain time, okay, and amount of the metabolite excreted in the urine cumulative, okay, and we have this, okay, this profile is the amount of the drug available to be absorbed or at the absorption site, which is XGI, which is the same as DGI, okay? And we still have one thing that is not shown here, which is okay, and we can have it until, which is the amount, the amount of the metabolite that is in the body at certain time. Similar to the profiles that we explained before and the IV, but the difference that the whatever that we have in the body is different in shape. We have this is extra, but those are still behaving similarly because we are measuring it either in the urine or in the blood. Okay, so for the absorption model that we have, we will talk about the amount of unchanged drug or metabolite can be measured in the urine. First of all, we will have one compartment. We will talk about it when we talk in details about the kinetic. We will have one compartment, so we can measure the drug and the body, and we can measure the unchanged drug or metabolite in the urine. And drug and metabolite in the body are measured in concentration unit, and that's what you know already, that we measure the concentration in the blood or plasma or serum, because we can't measure it. The direct the direct measurement of the drug at the site of the administration or even the site of absorption is not practically feasible in this model, and this already we know it, and we discuss it in the introduction of the kinetic course, in which you can't do it directly. That's why we have one of the major assumptions that we talked about earlier, that the concentration of the drug at the biological fluid, which is usually the blood, at equilibrium with the concentration of the drug at the site of action, tissues, or organs. Because why is this? Because the measurement at this site is not practically feasible, so we depend on this to indirectly know whatever is happening here, which is the kinetic homogeneity of a principle. Okay, so those kind of things that you already know. We will talk a little bit about the factors that could affect the absorption when we are talking about oral administration of the drug. It could be a physiological factor that is related to the site that we are talking about. Okay, so it could be physiological factors such as the membrane physiology, the GI different physiology, physicochemical properties of the drug that is correlated to the pKa in addition to the pH of the site that we are talking about. So it will affect the ionization of the drug, the lipophilicity or hydrophilicity of the drug, the molecular weight, the dissolution and solubility, which is also related to the formulation. Again, this is the definition or factors that would affect the absorption, right, at the site of absorption or a different site, which is what we call it the, and you know that we call it the biopharmaceutics of the drug. Okay. For physiological factor, we know that the membrane the membranes in the physiological system, they are lipophilic in general, and in nature, whatever the membrane that we are talking about. But if you are talking about oral administration, so we are interested with the membranes of the GI, and whatever is separating the GI lumen from the systemic circulation. So the nature of the membranes would affect the absorption and the nature of the absorption process. So if we are talking about the membranes, we know that they are lipid bilayer in nature, and they allow the transport of a small material, small molecule or uncharged molecules to go through with a little bit of the soluble either solvent or material to go through the membranes, right? Because it's lipophilic in nature as a membrane. So that's why, according to the lipid bilayer theory, which is which is saying that the membrane is consisting of lipid bilayer, we can explain how the lipophilic or small material can go through the bilayer, but ionized or large charged or electrically charged or non-charged, if it's large in size, they can't pass. Okay, this is the lipid bilayer theory. But we know, according to the studies, that there are some material that may go through the membranes, even if they are not from those, let's say, groups. Okay, and this is what goes under the fluid mosaic model, in which we know that there is some fluidity in the membrane, and there's certain kind of movement and pores available in the membrane. So we could have some movement of other material that is related to the pores, or related to transporters, or even related to the movement of the bilayer or parts of the bilayer. We know also that we have, other than simple diffusion, we have channels or transporters, or something related to energy dependent or energy independent. We have carriers, we have pores. Everything that is related to those kind of materials, or those kinds of transport or pass or uptake or distribution or passing of those materials through membranes, would affect the absorption of the drug. So all of those kind of details, which is related to the physiology of the membrane, okay, and the physicochemical properties of the drug that goes with one of those processes or the other, it's related and affect the absorption of the drug. And as I mentioned, the physicochemical properties of the drug, in addition to the membrane or the environment physiology, would affect. We know that the pH at different sites of the GI is variable. Even the cellular pH is usually 7, with the pH of the physiological pH of the systemic circulation is 7.4. So we know that changes of the ionization of the drug between different compartments here, or let's say different side of the membrane in addition to the membrane, would affect the status of the ionization. And if the status of ionization is different, then the absorption of the drug would be different. We know that the transport could go through the spaces, the aqueous spaces between cells, that's called paracellular transport. It could go through the cells, whatever the way, either passive or active, through pores or through molecules, and could be using different ways or transporters or molecules, and it's called transcellular. And from the name, it's going through the cells rather than between the cells in paracellular transport. Okay, as I mentioned, the pH at different sites of the GI is different. It's acidic, and the stomach then start to increase, and the small intestine, different parts of the intestine, until it's around 8 in the ileum, which again, when we go to large intestine, is decreased. So changes in the pH of the environment that we are talking about, the physiological environment, would affect the ionization of the drug. And if it's affect the ionization, it affect the absorption of the drug by different ways. Okay. And in those two slides, you know that according to whatever we are talking about, the stomach or small intestine, the absorption would be different, either if it's related to the pH, either to the movement of the stomach or movement of the small intestine. It would affect if we are talking about a fed state rather than fasting state, the liquid that we have, the temperature that we have, the viscosity of the material that is inside, even the, which is very important, the sectional area of the side that we have of stomach rather than the small intestine. You know that the surface area and one of them is larger than the others, so the absorption, if it depends on the surface area or sectional surface area, would be larger in one compared to the other. Okay, and